Hello everyone and welcome to this 7th lecture in the course titled Solar Photovoltaic System Design. So today we will be looking at the application of what we have studied in the last couple of classes, and we'll be talking about the plane of array solar radiation estimation. So this is an extension of what we started in the last class. So if you recall, in the last class we started talking about this plane of array solar radiation, and we looked at the three major components. So we have direct radiation or the beam component, we have the diffuse radiation which comes due to the scattering of radiation by the atmospheric particles, and then you have a ground reflected radiation. So we have these three components of radiation coming in the plane of array, and if we want to estimate that what is the fuel which is input to our PV panel, then we need to estimate this plane of array radiation, and based on that plane of array radiation the output of the PV panel would change. So as we mentioned in the last class, we will be looking at a simple Liu-Jordan model which is isotropic transposition model, and this is how the beam component is modeled in that particular model. And if you remember, last class we talked about one very interesting simplification of this. So if you are in the northern hemisphere, then the ideal tilt angle for your solar PV panel beta is equal to the latitude of the location phi, and your module azimuth is 0 degree. That means you place your panel facing due south. And at the end of the lecture I had given you a small homework to find out what should be the simplification for the southern hemisphere. So with in the northern hemisphere we saw that with these two assumptions, which are the standard assumptions for in the northern hemisphere, this complicated equation gets simplified to B equal to dni cos delta cos HRA. And I had given you the task that if in the southern hemisphere these standard assumptions are beta equal to minus phi, tilt angle is same as the magnitude of the latitude, but because of the sign convention in the southern hemisphere the latitude is negative, so the tilt angle will be negative of that value, which will be positive, and your module azimuth or psi will be 180 degree, because in the southern hemisphere one has to place the panel facing due north. So I hope you would have tried this interesting simplification, and interestingly if you implement these two assumptions in this particular equation, then interestingly this equation again simplifies to the same equation B equal to dni cos delta cos HRA. You can try it for yourself if you have not done already. So that is very interesting. So whether you are in the northern or the southern hemisphere, if you take the standard assumptions for the tilt and orientation of a PV panel, then you get this simplified equation irrespective of whether you are in the northern or the southern hemisphere. So now as we can see, probably these two particular variables, they come out as the most critical ones for determining the beam component. So the delta indicates the declination or the solar declination, and HRA is the R angle. So in today's lecture we will look at these two angles in little more detail, try to understand what these angles are and how to interpret them and how to evaluate them. So let us start with the declination angle delta. So the declination angle, which is denoted by delta, it varies seasonally due to the tilt of the earth on its axis of rotation and the rotation of the earth around the sun. So there are two phenomena which have been mentioned here. So one thing is that, let us say you have the sun here and you have this say as the orbit of the earth around the sun. So one thing is that the earth is going around in its orbit around the sun, and interesting thing, another thing is that there is this tilt of the earth's axis. So the axis of the earth on which it is rotating, it is not vertical, it is tilted. As we know, the angle of tilt is around 23.5 degree. So if the earth were not tilted on its axis of rotation, the declination would always be 0 degree. However, the earth is tilted by this angle of 23.45 degree, and therefore the declination angle varies plus or minus this amount. How does it vary? Let us look at it in little more detail. So I will come to this figure in a short while, but before coming to this figure, let me explain this little more detailed figure. So let us say this is the sun and you have the earth's orbit around it, which is slightly elliptical in nature. So this is the earth's orbit around the sun. Now, as we mentioned that Earth is going around in a moving around the sun and rotating on its axis with a tilted axis. So, what happens here is that, as you can see, as the Earth will go around like that, and one more thing let me indicate is the equatorial plane, the equator on the Earth, the equatorial plane somewhere like that, passing through the center of the Earth. Now, interesting thing is that if you see this, the sun is directly overhead at different parts of the globe or the planet Earth at different times of the year. So, as we know, this is the northern hemisphere, southern hemisphere. The north of equator is northern hemisphere, south of equator is the southern hemisphere. So, if you see especially these two positions, let us say I call this position 1, this one as position 2. So, if you see in position 2, the sun's rays are falling directly over the southern hemisphere, whereas in position 1 the sun's rays are directly falling on the northern hemisphere. So, these are two solstices. So, position 2 is also what we call as the winter solstice, when the sun is directly overhead on the southern hemisphere and at its extreme value. So, if you look at it from a geocentric perspective, that means from human perspective as an observer situated on this planet Earth. So, as we understand that sun is the center of the solar system and Earth is going around it, but because it is a relative motion, so for an observer on the Earth, it appears that the sun is moving in the sky. So, there are two movements of the sun, one is east to west, which we see every day. East, the sun rises in the east and then gradually goes up in the sky, then it sets down in the west direction. But as I mentioned in a previous class also, that the tilt angle or the elevation at which this east to west movement of the sun happens, that elevation angle keeps changing around the year, and that variation is in a north south direction. So, for an observer on Earth at different times of the year, the sun would be taking different height in the sky. Sometimes it will be more northwards, sometimes it will be more southwards. So, that is what is being captured here. So, for an observer in the northern hemisphere, the maximum the sun goes to the south is on this day, which is winter solstice, which is December 21 or 22 depending upon different preferences. And another one is the summer solstice. So, we are calling winter and summer with respect to an observer in the Earth, with respect to an observer in the northern hemisphere. In the southern hemisphere, the seasons would be opposite. So, in the northern hemisphere, December is the winter time and summer is from May to June, July. So, this summer solstice happens around June 21, and that is the maximum when the sun would come northwards. Now, the same, so this is basically the root of the explanation or the concept of declination angle. And now the same concept here is put here in these figures. So, I wanted to put it through an elaborate orbit diagram so that you understand better. And now, if you look at this diagram, so this is basically the same concept in a summary way. So, you have, this is the position 1, which is the summer solstice, when the sun is northward or at the northernmost point with respect to an observer on the Earth on the northern hemisphere. And this is position 2 or the winter solstice, when the sun is southwards or southmost point with respect to an observer in the northern hemisphere. And in between you have the equinoxes, where the sun is directly over the equatorial plane. And as you can see in these figures, we are defining declination as this particular angle between the beam of radiation from the sun and the equatorial plane. So, that is how the declination angle is defined. So, if I want to formally define, I would say declination angle is the angle between the beam radiation of sun and the equatorial plane. So, that is the angle delta, and as you can see, on summer solstice it will be maximum in the north and its value would be positive 23.45 degrees. On the winter solstice it would be maximum to the south, its value would be minus 23.45 degree, whereas at the equinoxes it will be directly the beam radiation would be in alignment with the equatorial plane and the value would be 0 degrees. So that is the variation of declination angle. The equation for this is this one here. So as you can see, this is the equation for declination angle. So you have delta equal to minus 23.45 degree, which is the value around which the motion is happening, and then multiplied by this cosine of 360 by 365 multiplied by d plus 10. So as we understand, d is here the day of the year. So January 1 will be d equal to 1 and December 31st will be d equal to 365, and any day in between you can calculate the d value. And now also it should be very clear, I mean it was inherent implicit in the explanations also, but especially looking at the equation, it should be very clear to you that declination angle is a global angle. It does not change with the location. So for the entire planet there is just one declination value on a given day. It only changes with respect to the day of the year. On a given day there is one value of declination angle, and the same is true irrespective of whether you are located in the northern hemisphere or southern hemisphere, near the equator, near the poles, wherever you are. So that is the declination angle. And if you look at its variation, we can plot it across the year with respect to day number, and maximum positive happens somewhere around the summer solstice around June 21, and it goes to 23.45 degrees. The maximum negative happens somewhere here around December 22 or the winter solstice, and again the value is minus 23.45 degrees. It crosses 0 somewhere here at the equinoxes. These are the equinoxes. So these are the two equinoxes, and in between the peak is at summer solstice, the negative peak at winter solstice, and this is the what we call as the autumn equinox, and this is what we call as the spring equinox. So that is the variation of the declination angle. Now let us go to the other angle of interest, which is the R angle. So to understand the concept of R angle, we will have to delve into a different aspect of the Earth's motion around the sun. Declination angle, as we saw, was mainly coming due to the revolution of the Earth around the sun. On the other hand, R angle is mainly coming into picture due to the rotation of the Earth on its axis. So as it says here, the definition says the R angle converts the local solar time into the number of degrees which the sun moves across the sky. Again, the sun is not moving, we know, but we are talking about this from a human perspective, from a geocentric perspective for an observer situated on the planet Earth. So by definition, the R angle is 0 degree at solar noon. Since the Earth rotates 15 degree per hour, each hour away from the solar noon corresponds to an angular motion of the sun in the sky of 15 degree. This is very simple, basic geometry if you apply. So let us say this is the Earth, and as we know there are latitude and longitudes. So longitudes are the vertical demarcations from north to south demarcations on the planet, which we have done for ease of locating any location on Earth. So as we understand, like this there are 360 degrees of longitude, because Earth is almost a spherical body. Now for Earth to rotate on its axis to complete a full rotation, it takes 24 hours. So in 24 hours it covers 360 degree of rotation. So what it means is that in 1 hour it will cover 15 degree of rotation. So that is what is being mentioned here, that for every hour the Earth rotates by 15 degrees. And another important thing here is that we are defining this term known as solar noon, and also if you see local solar time. So we should be a little bit cautious about these two terms, that is very important. So what is solar noon? So solar noon is defined as the time at which the sun is directly overhead a particular meridian or longitude. So that is very interesting, you have to be a little careful. The sun might not be directly overhead at your location, but if it is overhead your longitude at anywhere in the north south spread of that longitude, then that is the solar noon. Suppose we are talking about around the winter solstice. So we know that the sun is directly overhead in the southern hemisphere. So let us say at particular time of the day the sun is directly overhead this particular longitude, whatever we call it as L1. So let us say at some point of the day, because as the Earth is rotating, at some point of the day the sun will be overhead on each longitude. So at some point of the day, the sun is overhead this longitude L1. Now at that instant when the sun is overhead on this longitude L1, now for all locations which are at this longitude, that is the solar noon. So you need not be at this location. If you, even if you are here or near the North Pole or wherever or near the South Pole, for all the locations on this longitude, that is the solar noon when the sun is directly overhead on that longitude. So that is how we define the solar noon. Another important term here is the local solar time. Now we have talked about, we know, all of us know about time, we keep time through our watches and clocks, but then what is this concept of local solar time? So that is also, this is linked with the solar noon. So we need to look at it in little more detail. So we talk about time, we know about time, right? So we have watches, we have clocks through which we look at time. Now the time which we look at in the watch or the clock time is slightly different, or maybe sometimes maybe same, but for most of the people it is slightly different from the local solar time. And why does it come into picture? Because mainly if you see at this concept, because the earth is continuously rotating and at different times the sun will be overhead different longitudes. So that means whenever the sun comes over your longitude, that is your solar noon. Then after some time sun will be overhead on other longitude, that will be their solar noon. Some other time it will be over another longitude, it will be their solar noon. So that way the time is continuously shifting. But then for human interaction, it would be very difficult if everyone is having their own time. So to ease out human interactions and to ease out the way we measure and standardize time, what we have done is that we have done a little adjustment. So in a given country, we take one standard time. There are some exceptions to it. So like you have the United States or the bigger countries like Russia, which have a huge geographical spread. So for them, because the east to west spread is very long, so they take different standard times within the same country. But most of the countries, they have the same standard time. So suppose if I make a rough map of India, just for the sake of explanation. So something like that, we have the map of India and going southwards, and so a rough map of India. So now east to west we have a huge spread. So our westernmost part somewhere around 68° east, whereas easternmost part somewhere around 92° east. So we have a huge east to west spread. So if every longitude would to have their own time, then it would be very difficult to communicate about time with respect to each other. So that is why we need a standard time. So in India, the standard time meridian passes through Prayagraj in the state of Uttar Pradesh, or other parts also it goes through. So this is around 82.5° east longitude. So this longitude 82.5° east is what we have adopted as the standard time meridian for India. So when the sun crosses this meridian of 82.5° east, that is the solar noon for that meridian, but then entire India considers that as the noon time. So when your watch or your clock shows 12 noon, it is actually the solar noon of this meridian 82.5° east. But if you are on the east of this meridian, then for you, because with respect to an observer on earth, we observe that for us the sun appears to be moving from east to west. So if you are to the east of the standard time meridian, let's call this standard time meridian as the LSTM, local standard time meridian. So if you are on the east of this, for you the sun would have crossed your particular meridian earlier. So you will be ahead of this standard time meridian. So when the clock is showing 12 noon here, and entire India we have the clocks tuned to this particular time. So this particular portion, the eastern part of the country, will actually be ahead. It will be ahead of the solar noon at that point of time. Whereas in terms of the solar time, if you see the western part of the country, this will be behind. So this particular part would be behind. When your clock is showing 12 noon, then this portion might be at, let's say, 12:10 or 12:30 or whatever, whereas the western part might be still at 11:40 or 11:30 or 11:50, something like that. So there is a difference between the solar time and the clock time. So let's say I call this time with respect to the local standard time meridian as the local time. and the solar time as the local solar time, in short LST, and this is LT. Or to ease out the confusion so that it does not create confusion for you, you can maybe just call it simply as the local time meridian, LTM and LT, because they correspond, they appear similar, whereas LST is the solar time. So now what we can say is that we need to correct for time. So the local solar time, which you do not know, we do not know, because our clocks and watches are tuned to the time meridian of the standard time meridian. So what we see in the clocks is the local time, what we are calling. So LT is the clock time, and plus we need to have some time correction divided by 60, because time correction. So why we have divided by 60? Because the local solar time we are measuring in hours, the local time also we are measuring in hours, whereas the time correction we will put in minutes. So we need to do some time correction to correct this particular difference. And how to do that? Now again, that is not very difficult, it is pretty easy, it is nothing of a rocket science. So as we looked at in the last slide, in 1 hour your planet is rotating by 15 degrees of longitude, or in other words we can say in 60 minutes it is rotating by 15 degree of longitude. So for 1 degree of rotation it will take 4 minutes. So to go from one longitude to the another longitude, as the sun moves from one longitude to the next longitude, it takes only 4 minutes. That means for every degree of longitude there is a correction of 4 minutes which is needed. So therefore this time correction we can say is 4 times the longitude at which you are located minus your local time meridian, LTM. So in India this LTM will be 82.5. So we will have 4 into longitude minus 82.5 for Indian conditions. Other countries they will have their own standard time meridian. So now for example, suppose if you are located at 87.5 degree east in India. So for you it would mean 87.5 minus 82.5 is 5 degrees. So your time correction would be 5 into 4, which is 20 minutes, and it is positive, sign is important. Your solar time is 20 minutes ahead of the clock time. That means when your clock is showing 12 noon, actually your solar time is 12:20. And same way, suppose another example, suppose someone is located at 77.5 degree east longitude in India. So for them this is again minus 5, so for them the time correction would be minus 20 minutes. That means when their clock is showing 12 noon, then their actual solar time is only 11:40 am. So that is how we convert the clock time or the local time into the local solar time. And once we have the local solar time, then we can calculate the hour angle. So the hour angle is given as we looked at this definition, at solar noon it is 0 degree, and for every 15 degree motion of the earth, rotation of the earth, it moves by 1 hour. So basically your hour angle HRA is nothing but 15 degree into local solar time minus 12. That is how we define the hour angle. So when you have, and mind you this is the solar time. So when we have the solar noon, at solar noon LST equal to 12, because it is the noon time. So when LST equal to 12, your HRA is 0 degree. When your local solar time is 1 PM, that means so at 1 PM LST will be 13, and this 1 PM is the solar time we are talking about. At 2 PM solar time LST becomes 14 and corresponding HRA becomes 30 degrees. At 13 it will be 15 degree HRA. So that is how we calculate the hour angle. However, there is a little more addition to it, because this is the main concept, but then there is one little addition that I will introduce now. So we first calculate the local solar time by taking the time correction into account, and then from local solar time we can estimate the hour angle. However, there is a little matter of detail which is just there because of few factors, we look at it, and there is something known as little more correction. So main correction is this, which is basically due to the difference between the time meridian which is taken as the standard time meridian and your longitude. But then there is one little more correction which is known as the EOT, or equation of time. So time correction actually has one more component, which is the EOT. So instead of the equation ending here, it actually ends like this. And let us see what is this EOT, or equation of time. The equation of time is again measured in minutes, and it is an empirical equation that corrects for the eccentricity of the Earth's orbit and the Earth's axial tilt. So again, the Earth's orbit is not perfectly spherical, there is slight eccentricity, it is slightly elliptical, and the Earth's axis, as we just now discussed, is not vertical, it is tilted at 23.5 degrees. So due to these two factors, there is this empirical equation which has been derived. We will not look at the derivation of this, this is from the empirical observations. So we have the EOT given as 9.87 sin 2b minus 7.53 cos b minus 1.5 sin b, where b is given by this equation 360 by 365 into d minus 81, and d happens to be the same the day of the year. So on January 1 d equal to 1, on December 31 d equal to 365. And with this, when you put that d as the day number, then the b which you get here, capital B, that is in degrees. You have to be careful about that also. Sometimes students confuse between degrees and radians, but here the b which you get will be in degrees, and that b you put in the EOT, and you can find out the equation of time correction on a given day. And again, as you can see here, this is irrespective of the location. So whether you are in the northern pole or equator or southern hemisphere, wherever you are, the equation of time value or time correction with respect to this factor is same for everyone on a given day. And the variation, because it is composite of 3 sinusoids, as you can see, it looks like a complex sinusoid curve, not a simple sinusoid, and this is the variation. If you solve it out, you can verify and cross check that if you put the x axis as the number of days since the start of the year, then the equation of time in minutes varies like that. The most negative it goes is around minus 15 minutes, which happens around d equal to 45 days, whereas the most positive it goes is around 16-17 minutes and happens around this particular time around d equal to 300. So you can estimate the EOT and add it to the time correction equation to get the overall time correction, and then from time correction you go back to local solar time and then to the R angle. So that is how we estimate the R angle, and once you have the R angle, then you are good with the beam component. You can estimate B equal to dni cos delta cos HRA if you have the standard simplifying assumptions. If you do not have them, then you can calculate this equation also, because you already talked about phi, beta and psi, and you have HRA and delta. So even if you have non-standard tilt and orientation, you can evaluate the beam component from this equation as well. Now before we end today's class, let us quickly look at the other two components as well, because as you recall, we talked about the 3 components. The plane of array radiation is composed of beam plus diffused plus reflected. So the bulk of work which we so far discussed is the beam component. Diffused and reflected radiation are fairly simpler to estimate. The simplest is the diffused radiation actually. So for estimating the diffused radiation, as we said, we are using an isotropic model. So isotropic transposition model, that is what we are using, and that is the family of model which we are using, and specifically we are talking about the Liu Jordan model which we are using for our estimation. So as I mentioned earlier also, isotropic means, iso means equal, tropic means direction. So we are assuming that equal amount of radiation is coming from all parts of the sky, and that simplifies the calculation to a large extent. So if with that assumption, now if you have a flat lying module, then it receives the radiation from the entire sky globe. So from the entire sky hemisphere it receives the radiation like that. So the full, this is what we call as the DHI, diffused horizontal irradiation. On a horizontal surface, what is the total diffused radiation coming from the entire sky hemisphere. Now our fixed tilt panels, they are, as we discussed, they are at a particular tilt angle beta, they are not placed horizontal on the ground. So if you have your panel at a beta tilt angle, now it is fairly simple, as you can look at this particular diagram. So this portion of the sky which is behind the panel, so to say, which is shown in shaded in the dark color, that is sort of cut off from the panel. So this portion of the sky, that is not able to influence or the diffused radiation from that particular portion is not able to come to the panel. In this condition, the panel receives diffused radiation only from the portion of the sky which it is facing till this point, not beyond that. So we can say simply that your D in this case will be dhi into the factor 180 minus beta divided by 180. So if it is lying flat, it was receiving the diffused radiation from the entire 180-degree hemisphere of sky. If it is tilted at beta degree, then it is receiving the radiation corresponding to only 180 minus beta portion of the sky, and therefore D will be nothing but dhi into 180 minus beta by 180. So diffused is fairly straightforward. Then we go to the reflected component. The reflected component will not go into the derivation of this. It is slightly lengthy and we do not have much time in this course because we need to talk about other topics also. So we will directly use this result here. So it is nothing but ghi by 2 into 1 minus cos beta into albedo. ALB stands for the albedo. Albedo is nothing but the ground reflectivity. So how good is your ground surface in reflecting the radiation incident on it, because we are talking about the ground reflected radiation, and beta, as we already talked about, is the tilt angle. Now if you have the ghi, it is a very simple equation, just ghi by 2 into 1 minus cos beta into the albedo. If you do not have ghi, then you can estimate the ghi from the dni and dhi, as we looked at it in a previous lecture also, that your ghi is nothing but dni into cos of solar zenith angle plus the dhi. And as far as the albedo values are concerned, there are some standard values which are taken with respect to the different types of surfaces. So some surfaces are having a very high reflectivity. The best ones are snow covered surfaces, as you can see. If it is fresh new snow, it has a very high reflectivity, almost 80 to 90% of the radiation it reflects. If snow becomes little older and it is, dust accumulation happens, it is not so much white, then the reflection factor is in the range of 0.45 to 0.7. Then other standard surfaces like grass, concrete, lawn, woods and asphalt, they have different values. So if you have a road, asphalt road, it is 0.15. If you have concrete surface which is slightly old and weathered, it is 0.2. If you have clean concrete, it is 0.3 and so on. And usually when we do the estimation for, especially for a rooftop PV system, then definitely we go for this value 0.2 concrete weathered. And usually for our utility scale plants also, because as you can see the other numbers are also in the same range and we want to take a sort of conservative estimate. So this albedo value of 0.2 is sort of considered as a default value for solar PV installations if nothing else is given. If there have been some particular specific measurements at a location due to which a particular another value of albedo is recommended, then you go for that value. Otherwise, we just go for this particular value of 0.2. And this solar zenith angle, a brief little bit on that also, will not go into much detail, but just because we are using that solar zenith angle for ghi calculation, so we should also mention that particular angle. So zenith angle is nothing but the angle which the sun's ray or the beam radiation makes from the vertical. So zenith angle and elevation angle are complementary angles. Zenith angle we measure, we call it, denote it as theta z or sometimes as zeta also. And the elevation angle or altitude, we usually indicate it as alpha. So your zeta plus alpha is always equal to 90 degree, they are complementary angles, and again we will not look at the derivation, but we will use this particular result. So if you want to estimate the solar zenith angle, you can use this trigonometric identity, and alpha or the elevation angle is sine inverse of sine delta sine phi plus cos delta cos phi cos hra. And as we already discussed, delta is the declination angle, phi is the latitude angle and hra is the r angle. And once you have the alpha, you can find the zeta or the zenith angle, and then you can use it for estimating the ghi. So that is how we can calculate all the three components, beam plus diffused plus reflected, and we can get down to plane of array radiation. So before I end this class, I will give you this particular problem which you should try on your own. This is just some sample data I have put here for the location of Roorkee, because we are located here in IIT Roorkee. I have given you the latitude angle, which is 29.85 degrees north, longitude is 77.89 degree east, timing 3:15 p.m. on 20th April 2015. and the irradiation DNI is 510 watt per meter square, the DHI is 225 watt per meter square, and you have to estimate the irradiation on a tilted PV panel located in Roorkee, tilted at the optimal tilt angle for the place and oriented due south. So that is the problem you should think about and try to solve with all the equations which we have given here. And in the next class, we will look at the detailed solution for this problem. Thank you.